Okay, so let's first try to do part A, which is the Cartesian approach. So what do we normally have to do in the Cartesian? By definition, we know that the moment about a point is usually the position vector cross the force vector, right? And then if we want it on a particular axis, for example, the moment, say, about the x-axis, then what do? We would take some unit vector in the x direction and dot it into that cross product. So that's our strategy. So what we have to do now is first find a position vector that goes from any point on our axis, which is convenient because our axis x, y, and z, a common point, a collinear point, or a concurrent point would be the origin, point A. So I can find a position vector from A to anywhere on the line of action of the force. We don't have too many choices here. The line of action of the force, the only point that's actually given is B. So let's first quickly find the position vector from A to B. It'll be the coordinates of B minus the coordinates A. So in the x direction, it moves what? 4. It'll be 4I. In the y direction, it's 3. And in the z direction, it looks like it's minus 2. Everybody see that? And that should have units of feet. Our force vector is given. I'll just rewrite it here since it could be a little small for you guys to see. It's 4I plus 12J minus 3K, and that's going to be to form that cross product and then dot it into whatever axis we're looking at. That makes it pretty easy because our axes are just x, y, z. So what's the unit vector for the x-axis? I. So if I want to find the moment about the x-axis, I form my product. Remember, it's determinate, and it would just be 1, 0, 0. That's the components of the unit vector, which will just be in the x direction. Then my position vector, 4, 3, minus 2, and then my force vector, 4, 12, minus 3. So that should be the moment about x, or the x-axis. Now remember, when we do the determinant, we isolate the first row and columns. In this case, the only term that's going to survive is going to be the first term associated with 1. So it's just going to be what? It's going to be 3 times minus 3 minus minus 2 times 12. That looks like, what is that? 24 minus 9? 15? Now the units were pounds in feet. Did I do that right? You guys like that?
I think we use that as a top line. That's like the dot product, and you end up with multiplying each one.
Right, so if I want the y-axis, I'm going to shift my unit vector to just the y component. So the y-axis. I guess I could have dotted, no, I won't say that. That's incorrect. So the y-axis would be the moment about the y-axis is going to be what? The only thing that changes in the cross product, the triple product, is if now I go to, I want the y-axis. Nothing. So no x, y, no z. Right, this is the triple, it's called the triple product. Triple crown, yeah. American Pharaoh. Actually, I was alive and saw the last couple of Triple Crown winners. I thought it was kind of common. It was like 74, 72, 73, 74, like 3 or 4 years in a row, and then 37-year drought. That was when I was in high school. I figured, what's the big deal? It seems to happen every year. And then it stopped happening for 4 decades. Yeah, but that dotting, you combine it all right here. So instead of putting ijk and getting a vector, so if I put ijk here, what would I get? I would get a moment vector about point A, produced by this force. And really, that's what the bottom 2 lines are doing. So when you go ahead and combine it with the dot product, then you put the terms of the unit vector, or the vector that describes the axis, in the first position. So in this case, for this one, you isolate the second one. Remember, the thing about the determinant is when you have the second term, the j term, it starts off negative. It just has a negative sign associated with it. So I'll have 4 times minus 3 minus negative 2 times 4, whatever all that is. So that's 12 plus 8, no, negative 12 plus 8 is negative 4, and negative is just 4. That sound reasonable? So that would be 4 pound-feet. I think I ran the negative through the whole thing. I think this came out to be negative 4, right? Because I got negative 12 plus 8, and then the negative takes that out. That's part of the definition of computing the determinant of the 3x3, is that the second term, that comes from the fact that you get a negative with the j component. That always is there. And then the last one, the z-axis. So the moment about the z-axis, our determinant will look the same, except it will be 0, 0, 1. Our position vector 3, 4 minus 2. Our force vector 4, 12 minus 3. So in that case, the only term that's going to survive in the reduction is the last term, the z term. So in that case, we get 4 times 12 minus 4 times 3. 48 minus 12 is 36. That's a pretty straightforward application of the process. So the previous problem we were talking about, what was challenging was the determination of this axis that we were trying to find. Here we had simple axes, x, y, z. Remember on problem 460, we had those shifted axes that were kind of messing with us. Any questions about that one? I think that one is more typical of what I would probably ask you to do. Oh, the Cartesian approach. This is the Cartesian, the scalar approach. Now in this particular case, I think the scalar approach is not so bad, and I'll try to draw a visualization here to see if you can see it. So in the x component of our force, you can see is 4I. So in the x direction, that force would be going in this direction and would basically be 4 pounds. Now, is this force in the x direction going to create any moment about the x-axis? No. Is it going to create any moment about the z-axis? Yeah. So what's the perpendicular distance between the z-axis and this force? Remember, it can extend along any line of action, the whole line of action. Yeah, it's going to be 3 feet. It'll be 12. And what else? It also creates moment about the y-axis, and the perpendicular distance from it is this distance, which is 2. You see that? See the way that works? I'll try to I'll draw, see if I can draw a box. So that should show you how all the distances relate to this force there. And what do you have to do? Well, I have a component now of this 4 pounds about the y-axis and about the z-axis. So I have to slowly accumulate those. So you'll notice that about the y-axis, which is this one, I have a moment of 4 times 2, and you can see there's my 4 cubed component. Well, the 4-3 would come from what else creates moment about the y-axis would be the z component. And the z component of our force is acting down, right, at 3 pounds. And if you extend that line of action all the way up, you can see it has a distance of 4, and there's the 4-3. So you just have to piece them together. Again, it's easier to see in 2D, it's a little harder to see in 3D. Well, now you have to pick a sign convention. We usually use right-hand rule, so you're looking at, if for example I'm doing the y-axis, I'm looking at counterclockwise around that would be positive. So once you make that assumption, then your force is going to cause either clockwise or counterclockwise, and that's the way the signs will work out. I always use the right-hand rule.
It's harder to, when you said that you go straight up in the middle, it's hard to say that.
Well, no, the great thing here is you have something to, what's the word I'm looking for? I guess correlate it to. You have the x and y, so you can use the right-hand rule, x, y, z. So we know z is going in this direction, so anything that's curling around z like this would be positive. And remember, so go ahead. You can also go y, z, x, so anything rotating this way, or I guess my hand's not really doing the right thing. But you can apply that positive curl right-hand rule around each axis and establish. And that's what you're gonna see here. So the total effect around the y-axis is positive, and you can see the z-axis is creating positive rotation around the y. And the x component is also creating positive rotation. If you add them up, you should get positive.
So C were positive because if it was going up, then that would be a negative. You can do a sign convention.
Yeah, yes, the Z would, yes. I drew these in the I think I drew them in the correct direction. Positive X and then negative Z. So sometimes it's just, I think it's problem dependent. In 2D, sometimes the scalar approach can be pretty easy to do. In 3D, it's more likely that the triple product will be easier to pull off. Okay, any other questions about that?